Hi everyone, this is Laurent. I will be attempting to solve problem 5, sample problem 5 in section 8.4.4 of the linear momentum notes. It is a problem that has two collisions in it, symbolized here by situations A, B, and C. So in between A and B we have the first collision, in between B and C we have the second collision. The first collision involves two blocks, 1 and 2, out of the 3. Block 1 initially goes at some speed towards the right. Block 2 is static. Block 3 is also static. During the first collision, blocks 1 and 2 impact, and after that, block 1 goes at some speed to the left or the right. We don't know, we must determine. And block 2 goes to the right at some speed. We don't know. Block 3 still hasn't changed. It wasn't involved. For the second collision, this one involves block 2 and 3. Before we have block 2 going at some speed towards the right, block 3 is immobile, and afterwards the roles are reversed. Block 2 is static and block 3 goes to the right at 5 meters per second. Block 1 wasn't involved in this collision, so its state doesn't change. We need to find three things. We need to find the masses of block 1 and block 2, and we need to find the final velocity of block 1. That is its direction and its magnitude. To do that, we'll need to write a system of 4 equations. 2 for the conservation of linear momentum of collision 1 and collision 2, and 2 equations for the conservation of kinetic energy for collision 1 and for collision 2. We are in the realm of perfectly elastic collisions, so we have those 2 conservation ideas that take place. Our first task is to write a system of 4 equations considering the 2 collisions that we have. I'll go collision by collision and write my 4 equations there. Collision 1 is in between states A and B. It involves blocks 1 and 2 only. Starting with the conservation of linear momentum, we are only in the x direction, so we can drop the vector sign and just consider the direction with pluses or minuses, plus if to the right, minus if to the left. We'll have momentum of block 1 situation A, block 2 situation A, is equal to the momentum after the collision, block 1 situation B, block 2 situation B. We know before the collision this block is static, V is 0, therefore its momentum is 0. The rest we need to write. And that's it. That's going to be our first equation. Conservation of kinetic energy. We have kinetic energy of block 1 state A plus kinetic energy of block 2 state A is equal to kinetic energy of block 1 state B plus kinetic energy of block 2 state B. Again, V2A is 0, therefore the kinetic energy is 0. We can rewrite this as, so 1/2 mv1a squared is equal to 1/2 m1v1b squared plus 1/2 m2v2b squared, where all I did was use the definition of the kinetic energy. I'm going to crunch this down up top and only keep lines 1 and 2. For the second collision, we do the same step. We consider now for the second collision from B to C, only blocks 2 and 3 are involved. Block 3 at the beginning is static, it has no momentum or kinetic energy, and block 2 at the beginning is static, it has no momentum or kinetic energy. So I'll skip a couple of steps, but this is what it looks like. And these are our equations 3 and 4. The initial momentum before the second collision of block 2 is equal to the final momentum of block 3. Initial kinetic energy is equal to final kinetic energy. Again, I'll crunch this. And so this is the answer to part A. We have a system of 4 equations all linked together. We have the 2 equations, conservation of linear momentum and of kinetic energy for the first collision in between blocks 1 and 2. We have the conservation of momentum and kinetic energy for the second collision in between block 2 and 3. For part B, we need to find m2, the mass of the second block, the one that's involved in both collisions. We don't have enough information for collision 1, so we can't use that. We need to go through collision 2 between block 2 and 3, and this is what I have rewritten here, equations 3 and 4 that are involved in collision 2. I can solve for v2b or for m2. My plan is to solve for one of those two variables and plug it into the other equation to then solve. Like we have a system of two equations with two variables, so it's relatively simple. Here we just do a bit of algebra to find what we need. From equation 3, we solve, for example, for v2b. We get the following expression. We then substitute this in equation 4. This is here, and we square it. And we notice a couple of different things. We see that we have a factor 1/2 on either side. It goes away. We see that we have a factor v3c squared on both sides. It also goes away. We have a factor m2 over m2 squared. So this one goes away and one of the squares of m2 goes away as well. And we also have m3 squared on the left-hand side and m3 on the left-hand side, which means that one of the two m3 squares is cancelled by the one on the right hand. We're left with the following, which means that the two masses, m2 and m3, are exactly the same. We conclude m2 is equal to m3 is equal to 6 kilograms by the problem statement. Here we can also find what the initial speed of v2 is by plugging this value back into the reformulation of equation 3. The intuition that two masses of equal value, when impacted elastically, all of the momentum of the initial one goes to the other, is correct with the math. Okay, part C. In part B we found m2, now we need to find m1 and then we'll be able to find its original speed way back when. To find m1, now that we know everything about m2 in between the two collisions, we have enough information to go and work with m1 and with the two equations from the first collision. As a reminder, conservation of linear momentum is here, conservation of kinetic energy is here. First step, starting from 1, we'll just rearrange a couple things and rewrite it. We have three unknowns here, but we can get away with getting rid of one. v1b is unknown, v1a is unknown, m1 is unknown. What I did here was I solved for m1, v1b, and then v1b because that appears in here, in my equation number 2. So I'm going to square this and then plug it in equation 2. And once we have that, we can cancel out the 1/2. Just to make it easier, we can expand this term and do a bit of simplification. Note that this is all supposed to be on one line. We can then simplify this term here and distribute the 1 over m1 that's left over into all the terms in the parentheses, and we'll get one final line. And this is it. Again, this is all supposed to be on one line. This should be on the right-hand side. We have some more things that cancel out here. For example, this m1 here, this stays here, this m1 goes away. Now what we see after that, we could rewrite it and it'd be easier. In fact, let's just do it fast. Alright, rewritten, we have the following. We see immediately that m1 v1a squared goes away, cancels out. We very much like that. The only thing that we don't know is m1. I mentioned earlier, I think I said that we didn't know what v1a is. I was mistaken. The problem description below says it's 10 meters per second to the right. So we know the value of v1a here. We then only have really one unknown. We can solve for it and then plug in our numbers, we'll get m1. And here we see that we have m2 on both terms of the denominator and it appears on the numerator. So we can cancel one out. We have also v2b that appears on both terms of the denominator and it appears on the numerator as well. We can also cancel one of those out. This simplifies a bit our algebra. And that's it. m1 is equal to 2 kilograms. For part D, we need to find the final state of block 1. We had found in part C this equation, v1b is equal to m1 v1a minus m2 v2b over m1. Since we know all of this, we can find what the speed of block 1 after the first collision is. And we find this here, v1b, the speed of block 1 after the first collision is negative 5 meters per second. We haven't made a mistake. This matches with the original system of axes that we had. Remember, this is the situation that we have in between the first and second state during the first collision. We said that the x-axis points to the right. Every velocity, every momentum that was pointing to the right was positive. Anything that is going to the left, we established was negative. Having a speed that has a negative sign in front of it means that the direction of the velocity vector is to the left. So we can write, and since block 1 isn't involved at all in the second collision, its state doesn't change in between part B and C. Well, we can conclude. And that's it.